Hi there, Mr. Sutton here, bringing you the BC Calculus Chapter 6 Quiz 3 Review Solutions on Euler's Method and Logistic Growth. On this problem, they are asking us to use Euler's method with two increments of equal size to figure out the value of y when x equals 1.8, given this differential equation, and f of 2 equals 1 is our starting point. So if I'm going backwards from 2 to 1.8 in two steps, I have to go by increments of negative 0.1. Okay then, let's start off by approximating f of 1.9, and then we'll use that approximation to get f of 1.8. So f of 1.9 is going to be approximately equal to, let's see, that's going to be f of 2 plus f prime of 2, and our step size of negative 0.1. So then f of 2, well, they gave us that, that's 1. And if I want f prime of 2, I have to plug 2, 1 into my differential equation. So that's going to give me, let's see here, 2 minus 2 times 1, which is 0. So then I have 1 plus 0 times negative 0.1, which comes out to 1. All right, I've got f of 1.9 figured out. Now I'm going to go all the way to f of 1.8. That was my real goal all along. So that ends up being approximately f of 1.9, which we just figured out, plus f prime of 1.9 times our step size of negative 0.1. f of 1.9 we said was approximately 1. And then f prime of 1.9, well, I'm going to have to do 1.9 minus 2 times the approximation for y of 1. So 1.9 minus 2 gives me negative 0.1. And that negative 0.1 is getting multiplied by this negative 0.1. So this is going to be 1 plus 0.01, which is 1.01 for our final answer. On this problem, we have this table of f prime values. We're told x is always positive and f of 1 equals 15. And they also gave us some f double prime for good measure there. They want us to use Euler's starting at x equals 1 to figure out f of 1.4. We're doing two steps of equal size. So that means we have to go by 0.2s. So our first thing we're approximating is going to be f of 1.2. Once we find that, we'll use that approximation to figure out f of 1.4. So this is going to be f of 1, approximately, plus f prime of 1 times 0.2. f of 1 they told us was 15. f prime of 1 is in the table, that's 8, times our step size of 0.2. So this is 15 plus, let's see, this is going to be 1.6, so 16.6. And now let's move on to figure out f of 1.4. That's going to be approximately f of 1.2 plus f prime of 1.2 times our step size of 0.2. f of 1.2 we approximated to be 16.6. f prime of 1.2 is in our table, that's 12. If we multiply that by our step size of 0.2, that would be, let's see, 24 with a decimal, one decimal place, so 2.4, plus 16.6 comes out to 19. For this problem, we've got a logistic differential equation describing the growth of a population of creatures. We want to find, first off, the carrying capacity of our population. So since this is in Kp times m minus p form already, our carrying capacity is just this m value here, this 400. So that's 400 creatures. That's the max level this population can attain. Next, they want the size of the population when it's growing the fastest. So that's always going to be half the carrying capacity. In this case, 400 over 2 gives us 200 creatures. And then they want the rate at which the population is growing when it's growing the fastest. Well, here is the when it's 200 creatures. So we just need to plug that when into p in our differential equation. Now, it's not really a time, but it's the population at the time that we want. So plugging in 200 for all those p values, we just have to do this out on the calculator now. So plugging all that in, we end up with a value of 48, and that's going to be creatures per year. For this problem, we're given this logistic equation here, describing the growth of a population of wombats. And we've got t measured in years. T is always greater than 0. So we want to find the limit as t approaches infinity of our population of wombats. We're basically asking about the carrying capacity, since this is a logistic equation, but I don't have this in standard Kp times m minus p form yet. And I know this because this p in here, this output variable, has something other than just itself. We have this divided by 40 business going on. So I'm going to take out a 1 over 40 to make my format something easier to work with. If I factor out 1/40th, that's going to be 20 over 40, or 1/2 out there, times a p. And inside, if I'm dividing everything by 1/40th, I'm really just multiplying everything by 40. So this is going to be, let's see here, this is going to be 20,000, or no, 2,000 rather, 2,000 minus p. There we go. So that means I have a carrying capacity of 2,000, which means my limit as t approaches infinity for these creatures is going to be this carrying capacity of 2,000. Next, I want to know at what p-value p of t has a point of inflection. So it has a point of inflection always halfway to the carrying capacity. So that's going to be a point of inflection when p equals 2,000 over 2, which means when p equals 1,000 creatures. And then finally, if p of 0 is 100, at what times is p prime of t greater than 0? So if we are starting below the carrying capacity, which is 2,000, and we know we're below because we're only at 100 here, then we're always going to be growing. This is always growing, even though it kind of levels off as it gets closer to that carrying capacity. So this would be from 0 to infinity then. Now, if our initial value were above the carrying capacity, then we would be decreasing the whole time. But we're below, so we end up growing.